Okay, first question. How much kinetic energy will an electron gain in both joules and in electron volts if it accelerates the potential difference of that much in a TV picture tube? Right. So the equations I'm going to rely on to solve this is at the bottom of the lecture notes, which I'll just write as a single equation here. That is, if you've got a charge moving from point A to point B in an electric field, then the change in electric potential energy of that charge will be equal to Q times the change in potential going from A to B, which is the same as the work done by the electric field on the charge and going from A to B. This will rely on a lot. Now let's apply it to question 1. So I've got my electron moving from point A to point B, and I'm given the potential difference between the 2 points. Now, first things first, is this plus 23,000 volts or minus 23,000 volts? It just says it's a potential difference of 23,000 volts. So I just written like this, it might be slightly ambiguous whether it is positive 23,000 volts or negative 23,000 volts. To eliminate that ambiguity, I think in terms of the charge Q, is it positive or negative? It's negative because it's an electron. And electrons, well, negative charges in general, tend to move from lower to higher potential, and positive charges the reverse. So VBA is just shorthand notation for VB minus VA, the change in potential going from A to B, what you end up with minus what you start with. And if the reasoning that it's an electron with a negative charge moving therefore from lower to higher potential, if this is the potential here at B is higher, if this potential is higher than this one, then this will work out to be positive. So I can reason this way, that this is plus 23,000 volts, not minus 23,000 volts. Okay, so now what are we after? We're after the change in kinetic energy, right? So the change in kinetic energy will be the net work done on the charge. Now what's the net work done on the charge? In this case, it will just be the work done by the electric field on the charge. It's just an electron, so we'll completely discount any gravitational effects. For example, of a problem where we don't discount it, I believe that was question 4 of the tutorial. So refer to each video where the net work done is not simply just the work done by the electric field. Okay, so now we just use the formula, and this is equal to minus Q VBA from the formula above. Okay, so you could also have reasoned that the change in kinetic energy is minus the change in electric potential energy, which is in other words also equal to this. So we could have gotten, could have gotten to minus Q VBA from this side instead of from this side as I just did. Okay, but now just substituting the values. This is minus 1. Well, am I going to just use 1.6 or 1.602? Well, how many significant figures do I have in the data that's given? Oh, my pen just fell. The 23,000 volt, it's not clear exactly how many significant figures that is. It could be just a 2 and a 3, or it could be the 2, 3 and the 0. Not sure. I'm going to assume it is like 3 significant figures, so that we're certain of the 2, 3 and the 0. But it's not clear exactly if it's written this way. So I'd rather use 1.602 times 10 to the minus 19 coulombs. So that's a charge of an electron. Okay, but it should be minus that. There's another minus there. Minus 1.602 times 10 to the minus 19 coulombs times the voltage, 23,000 volts. Okay, so let's calculate that. So 1.602 times 10 to the minus 19 times 23. Okay, so this is equal to 3.68 times 10 to the minus 15 joules. Okay, now the question is, also asks to provide this answer in electron volts. Now, what are electron volts? That is just explained at the top of the tutorial. It's just a different unit of energy. So there's 2 ways you can go about rewriting this as an electron volt. Now, when I say it's a different unit of energy, it's in the same way as saying that you have a different unit for measuring distance or for measuring mass or whatever. So it's like telling you to convert between inches and centimeters, or converting between kilograms and pounds, or between liters and US gallons. It's no bother, it's no problem to do that. In order to convert between them, you just need to use a conversion factor, and to work out the conversion factor, you just need to know how much of the one is how much of the other. So if you know that 1 pound is 0.4536 kilograms, then you can use that to work out to express the conversion factor. So likewise, let's say you have a certain let's say you've got a certain number of you have a certain energy value, let's say 23.7 times 10 to the minus 6 joules, doesn't matter, and you want to convert this to electron volts. Now, one way is just straight using a conversion factor. You know that 1 electron volt is this many joules. So you say, okay, if I want to convert this to electron volts, all I have to do is say I have to multiply for electron volts over joules. So 1 electron volt is 1.602 times 10 to the minus 19 electron volts, and calculate that to get your answer in electron volts. So this is one way, just straight up using the conversion factor. The other way is to understand what an electron volt is, in which case, for the problem that we're trying to solve right now, number one, you can immediately write how many electron volts there are without having to calculate anything. And to understand how it's defined, you have to look at this formula again. Look at this formula. It says that the change in potential energy of a charge Q that moves from point A to B, where there's different potentials, then the charge Q times that potential difference gives you the change in potential energy. Now, an electron volt is simply saying, look, the amount of potential energy that you would lose or gain if your charge was the charge magnitude was that of an elementary charge, in other words 1.602 times 10 to the minus 19, and if your potential difference was 1 volt, the amount of potential energy lost or gained in that case, let's define that amount of energy as 1 electron volt. So it's a much smaller unit of energy, which is more accommodating for cases like this where you're just working with an electron. So the amount of energy gained or lost when a charge with magnitude that of an elementary charge moves through a 1 volt potential difference, that amount of energy is called an electron volt. But look here, in this case already, I've got a charge with charge magnitude that of an electron volt. Specifically, I've got an electron, and it moves through a 23,000 volt difference. Now, if this was not 23,000 volts, if this was 1 volt, then then my answer would immediately be 1 electron volt by definition, directly by definition of the electron volt. If this wasn't 11 volts, if this wasn't 1 volt but it was 11 volts, then the answer would be 11 electron volts. If this was 211 volts, then it's a charge with charge magnitude that of elementary charge moving through a 211 volt potential difference, so then the answer would be 211 electron volts, just by definition of an electron volt. So what is my answer in this case? I've got a charge of magnitude that of the elementary charge going through a 23,000 volt potential difference, so this will be a 23,000 electron volt changing potential energy. Right. So you can immediately say that this is 23,000 electron volts just by definition of the electron volt. Or you can go with the conversion factor route to change between joules and electron volts. And you can see here that look at the value that we get for the energy if we use joules. It's this funny value. But the electron volts, which are much smaller and much more accommodating energy unit for small charges like electrons, get a much more digestible numeric answer for the energy. Okay, so it's just a different unit that is more accommodating for small charges and their energies when moving in fields and potential differences. By virtue of the way that it's defined in this calculation, you can immediately say what the amount of electron volts this many joules are. Okay, so this is the answer. Now, what I want to just revise again, because it's important we use it here, how we reason that it must be 23,000 volts, and why I said that if it's a negative charge, it moves from from lower to higher potential, but positive charges move from higher to lower potential. So I just want to go over that explanation again that we did in class, because it's very important. We often rely on it, and it's a very simple idea where it comes from. We can compare it to just a case of a rock. Let's say you've got a little rock there with a certain mass, I don't know what, and it is dropped from that height, and it falls to the ground. What happens in terms of potential energies? Here it's got a certain gravitational potential energy, and on its way down it transforms that into kinetic energy until it reaches the bottom here. So I don't know what the actual potential energy is here. To say what the gravitational potential energy is at this point, I've got to specify where it is zero. If it is zero here at this ground level, it doesn't have to be, but this is conventional to make it zero here at the ground level, then the gravitational potential energy would be mgh. But regardless of where we set it to be zero, one thing that will be the same always is on its way, it's starting from rest, and it is dropped, then from where it starts, it will have a higher gravitational potential energy than where it ends up going. So it moves in a direction that reduces its gravitational potential energy. Okay, so this is all familiar to you. Now, and it is because it is specifically with respect to the gravitational force which is working downwards on this mass. Now, just like a rock, when just dropped, it will move in a direction to lose its gravitational potential energy. Electric charges and electric fields do exactly the same. Let's say you've got a positive charge there, and you've got some electric field around it that is, let's say, in this direction, some electric field there. Then what is this charge going to do? It's going to move in this direction. We also assume it starts from rest. Okay, now, if it then goes into this direction, then just like for exactly the same reason that the rock has a higher gravitational potential energy here than it does here, for the exact same reason, mathematically, the positive charge will have a higher electric potential energy here than it does here. On its way from here to here, it loses that electric potential energy and transforms it into either kinetic energy or something else. It transfers it to another system in the form of work or whatever. For exact same reason. Let's say this is point A and this is point B. So this is point A and this is point B. So the potential energy, gravitational in this case, at A is greater than the potential energy here at B. And the same thing here. The potential energy at A is greater than the potential energy at B. Only here it is gravitational potential energy, and here it is electric potential energy. If it was an electron or just a negative charge, same thing, and let's say the electric field is I don't know, in this direction around it, then the charge will move in this direction. And let's say it is also A and also B, then for the exact same reasons as here and here, here at point A, the potential energy at A will be greater than the potential energy at B. Again, we assume that it is starting off from rest. And that is an assumption that we make. Otherwise, this might not be true. For example, you can throw a rock upwards into the upwards into the air, and then in the direction that it's moving, the potential energy will actually increase. So now we're not considering that. We're just not considering if it is starting from rest. Okay. So in all three cases, let's say the particle moves in a direction to lose its potential energy. But with charges, we think in terms not of potential energies, we think in terms of potentials. So now what are potentials defined as? For potentials, you divide by the charge. Now let's say this is a charge Q and this is also a charge Q. The difference is this one is negative and this one is positive. Here Q is positive and here Q is negative. Now, what is the potential? The potential is VA, but VA is what? VA is equal to the potential energy at A divided by little charge Q. Now, if I divide by a positive number, I've got these two things, this one greater than that one. If I divide on both sides by the same positive number, then the inequality does not change direction. Equal to VB. See, so the potential from going from A to B is still at A larger than at B. So for a positive charge moving from A to B, it will, if it loses its potential, electric potential energy, it loses potential. So it moves from a positive charge, moves from release from rest in an electric field, moves from higher potential energy to lower potential energy, and therefore, because it's a positive charge, it moves from higher potential to lower potential. But for an electron, it is the other way around, because now what happens if I divide here by the charge? Then the inequality sign switches direction. So in this case, the potential at A is less than the potential at B. It is, so the reverse happens. Just like for the positive charge, it moves in a direction to lose its electric potential energy. But by the way that we define potential, that means it's going in a direction to increase its potential. So it loses its electric potential energy, but it gains potential, or it's moving to a point of higher potential. Remember, potential is a property of the point in space, as opposed to the electric potential energy, which is a property of the system and of the particle itself. So here it has a certain electric potential energy, but it is at a point of certain potential. So see, because we're dividing here by a negative number, even though it is losing its electric potential energy, it is moving in a direction of greater potential. Okay, so this is where it comes from when we say that positive charges will tend to move in a direction of lower potential, from higher to lower potential, but negative charges will tend to move in directions from lower to higher potential, the other way around. And that is what I used here when I reasoned that this is 23,000 volts. It is an electron being accelerated in an electric field. So I reasoned that means it is going in a direction where it's losing its electric potential energy, just like when a rock or an apple is falling from a tree. And therefore that means that it is going from lower to higher potential. And that is how I ran the reason, and this is 23,000 volts. Okay, so this is just to explain again an important concept in this chapter, is why we say that positive charges tend to move from higher to lower potential, but negative charges move from lower to higher potential. Positive charges move from higher to lower potential, but negative charges to the opposite, they go from lower to higher potential, even though in both cases they'll move in it from higher potential energies to points where they'll have lower potential energies. Okay.